Hello everyone. Today I am going to discuss about the types of DC motors. Already discussed about shunt and series motor. So the types of DC motors. So DC shunt, DC series motor and compound motor. So in the last session we have discussed about shunt and series motor. The shunt motor is nothing but the field winding is connected in parallel with the armature, whereas in series motor field winding is in series with the armature. So compound motor is nothing but it is the combination of both series and shunt field winding. So in compound motor we have two types, one is long shunt and the other is short shunt. So in long shunt compound motor, the shunt field winding is connected in parallel with the armature and series field winding. So long shunt. So here the shunt field winding is connected in parallel with both armature as well as series field. That's why it is called long shunt. Here the total current is IL and it is getting divided into I shunt and I series. So IL equal to IA plus I shunt, where IA and I series are same because both are connected in series. So it is I series plus I shunt. So the voltage equation for this long shunt motor is can be written as V equal to EB So in this, we have two brushes. So the total brush drop will be 2 volt. Here the current through armature and series field is same because both are series connected. So I can replace I series as IA. IA and I series are same. So I can take IA outside. So EB plus IA into RA plus R series plus brush drop. So this is the voltage equation for a long shunt motor. Similarly, for short shunt, in short shunt motor, the field winding is connected in parallel with armature alone. That is, the diagram will be so in short shunt motor, the shunt field winding is connected in parallel with armature alone. So the current IL is equal to the series field current I series and shunt field current, that is the total current IL can be written as IA plus I shunt because the sum of the current flowing through the armature as well as the shunt field winding. So the voltage equation of this motor can be written as so here EB is the back EMF of the motor and IA is the armature current and I series is the series field current. Here the IA and I series is not same, so it can be written separately. So V equal to EB plus IA RA plus I series R series plus brush drop. Similarly, the brush drop can be considered as 2 volt because we are having two brushes, and based on the another one classification is cumulatively compounded and differentially compounded. Cumulative compound. Here in cumulative compound motor, if the series field aids the shunt field means then it is called cumulative compound. We are having two field winding, series field winding as well as shunt field winding. If both of them are helping each other, then it is called cumulative compounded motor, and the other is differential compound motor. In differential compound motor, if the series field opposes the shunt field means then it is called differential compound motor. So we have discussed about different classifications based on the connection of windings with the armature, whether it may be connected in series with the armature or it is in parallel with the armature. We have classified into three main types: DC shunt, DC series and DC compound. And the compound motor, here we have long shunt, short shunt, as well as another one classification is based on the field winding, that is whether it helps each other or opposes each other. We can classify it as cumulative compound motor and differential compound motor. So next is the characteristics of DC motors. In general, we have three different characteristics. One is speed versus armature current characteristics. Another one is torque versus armature current, and the other is speed torque characteristics. So here the torque versus armature characteristics, also known as electrical characteristics, whereas speed versus the torque characteristics, also known as mechanical characteristics. So here we have to discuss all these characteristics for shunt and series motor. For a shunt motor, so here so in shunt motor, we have the speed equation, N is proportional to EB by phi. So EB is nothing but back EMF of the motor, and it can be written as V minus IARA divided by phi. So where V is the voltage applied and IA is the armature current and RA is armature resistance and phi is flux. So here in case of DC shunt motor, first we have to discuss about speed versus armature current characteristics. So current will be taken in x-axis and speed is taken in y-axis. So shunt motor is also known as a constant speed motor. Its speed almost remains same. In ideal cases, it will be like this. But practically, if the armature current increases, so what happens means the flux also increases. So here, if the flux increases, the speed and flux are inversely proportional. So if your armature current increases positively, flux also increases, which means that speed decreases. So we have a reduction in speed. It can be written as, it can be drawn like this. So this is the speed versus armature current characteristics for a DC shunt motor. Speed and flux are inversely proportional because if we increase armature current, automatically flux also increases. So if flux increases, speed decreases because both are inversely proportional. So we have a slightly drooping characteristics. And next one, torque versus armature current characteristics. So in torque versus armature current, we will be taking armature current in x-axis and torque in y-axis. So the characteristics will be like this, ideal case, and the shaft torque will be like this. So the torque versus armature characteristics, also known as electrical characteristics. Here we are taking armature current in x-axis and torque in y-axis. So we know already T is proportional to phi into Ia, where phi is flux per pole and Ia is the armature current. In case of DC shunt motor, the flux remains constant. So torque is directly proportional to armature current. So if we increase the armature current, automatically the torque also decreases. So the curve is straight line from origin because directly proportional. So if armature current increases, the torque also increases linearly. So the curve is linear from origin. So next is speed torque characteristics, also known as mechanical characteristics of a motor. Here torque is taken in x-axis and speed in y-axis. So here in this case, if the torque increases, the speed decreases and the curve looks like this. So this is about DC shunt motor. In case of DC series motor, we have three different characteristics. One is speed versus armature current characteristics. So here also N is proportional to EB by phi. So EB can be written as V minus IARA by phi. So here we are taking armature current in x-axis and speed in y-axis. So in case of series motor, the winding is connected in series with the armature. So here the field winding is connected in series with the armature. So here if you increase the armature current means the flux also increases. So if the flux increases, automatically speed decreases. So the curve will be like this. So this is the curve for speed versus armature current of a DC series motor. So if you increase the armature current, automatically your speed will decrease. So the curve looks like this according to this equation, where V is the applied voltage, IA is the armature current, and RA is the armature resistance, and phi is flux. So if you increase the armature current, in case of series motor, T is proportional, that is the armature current is proportional to flux. So if you increase the armature current, automatically flux will increase. So if flux increases, your speed decreases. That's why the curve will be like this. And the next one is torque versus armature current. In torque versus armature current, IA is taken in x-axis and torque in y-axis. So here, according to torque equation, T is proportional to phi into IA. In case of series motor, the flux, because the field winding is connected in series with the armature, so that the flux is proportional to IA. So T is proportional to IA square, that is square of the armature current before saturation. So before saturation, torque is proportional to square of armature current. And once saturation is attained, here the flux remains constant. So T is proportional to IA after saturation. So before saturation, torque is proportional to square of armature current, whereas after saturation, torque is proportional to current, armature current. So here from origin, before saturation it will be like this, and after saturation it will be a linear curve. So this is for before saturation, and this will be after saturation. And next one, speed torque characteristics. So here we have taken torque in x-axis and speed in y-axis, and the curve will be like this. If we increase the torque, the speed starts decreasing. So it is inversely proportional. So we are taking torque in x-axis and speed in y-axis, and if you increase your torque, automatically speed decreases. And next one, compound motor. So in compound motor, the characteristics are obtained from both DC shunt motor as well as series motor. So already we have discussed about shunt and series. If it is a cumulatively compounded means its characteristics will be between shunt and series motor, whereas if it is differentially compounded motor means its characteristics will be away from the both shunt and series motor. So if we draw the speed versus armature current characteristics, armature current is taken in x-axis and speed in y-axis. Generally for a shunt motor, this is the speed versus armature current of a shunt motor. And then for series motor, it will be like this. This is for series. And for cumulatively compounded means it will be in between, cumulatively compounded. And if it is differentially compounded means it will be away from that. Similarly, in case of compound motor, torque versus armature current, if we draw by taking armature current in x-axis and torque in y-axis. If it is a shunt motor, the curve will be like this. If it is a series motor, the curve will be like this. So it is for shunt and it is for series. And for cumulative compound means it will be in between. So cumulative compound. And if it is a differential compound means it will so next is speed control of DC motors. Here, why we are preferring speed control in DC motors means wide range of speed control is possible in case of DC motors. So that is the main advantage of preferring DC motors for speed control. So here we have three different methods. One is flux control, another one is armature control, another one is voltage control. So we have three different methods: flux control, armature control, and voltage control. So flux control method, it is possible to obtain speeds above rated, whereas armature control method, we can get speeds below rated speed. So here for shunt motor, so here in flux control method, we have N is proportional to EB by phi. So EB can be written as V minus IARA divided by phi. So where V is the voltage applied and IA is the armature current and RA is the armature resistance and phi is flux. So by varying the flux, your armature current can be varied. If IA decreases means your speed will be above the rated speed. That is the main concept behind flux control method. So with the help of flux control method, speeds above rated speed is possible. So here it can be explained with the help of, that is, in flux control we can put a variable rheostat, so that here we can connect one rheostat like this. So what happens means the amount of current flowing through this rheostat will be determining the amount of current flowing through the shunt field winding. So if you reduce, if you add some resistance, means automatically the current will be decreasing. So if current decreases, the flux also decreases. If flux decreases, speeds above rated can be obtained. So with the help of this method, speeds above rated speed can be obtained. That is flux control method. And another one method is armature control. So in armature control, speeds below rated speed can be obtained. So here what we are doing means we are connecting one variable resistance in series with the armature. So the diagram for this will be, so here we have the resistance, so the amount of resistance added can be varied. If you vary the resistance, means automatically the current can be varied. If you increase the resistance value, the current is reduced, thereby the flux is reduced. If flux is reduced, means speed above rated can be obtained. That is the thing. So here in armature control method, T is proportional to phi into Ia. That is where phi is flux per pole and Ia is the armature current. So if the resistance increases, means current decreases. If the current decreases, the flux will be increasing. So if flux increases, what happens? The speed below rated speed can be obtained. So that is why this armature control method is called. That is this method which we can get speeds below rated, and also some amount of power is wasted in the rotor circuit. So that is the drawback of this method. Whereas in speed control with the help of flux control method, means it is a simple and inexpensive method. It is a convenient method. Whereas armature control method, some amount of power is wasted in the armature resistance, and also in this method speeds below rated speed is possible. இல்ல சார் பென்னு வேணும், எழுதவே இல்லை. இல்லையா?